Right. Okay. So my name is Zach Shuref-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I'd also like to introduce my colleagues and co-organizers of the seminar series. So we have Andrea Pizzaferato, who is an assistant professor at the University of Bath and an affiliate at the Alan Turing Institute, and also David Masugur, who is a new PhD enrichment student here at the Alan Turing Institute. And so for those who are not familiar with the Alan Turing Institute in London, this is UK's National Institute for Data Science and AI. Furthermore, for the benefit of those joining us for the very first time, I'd like to briefly introduce the topic of this seminar series. So that is physics-enhanced machine learning for engineering applications. So we hope that the seminar series is tailored towards an engineering and application-oriented audience. And physics-enhanced machine learning is an upcoming subfield in machine learning and deep learning that aims to integrate known physical understanding of observed phenomenon into machine learning frameworks. And of course, advantages include data efficiency, interpretability of the prediction model, which are of course vital criteria for engineering applications. And on a side note, if any of you are interested to share your work in this seminar series or in upcoming seminar series, please, I really encourage you to kind of get in touch with one of us through our website as well. And we have a nice nice sort of audience out there, and it would be nice to share your work as well. So as for the format of the seminar, so Cristian here will speak first, and then we will follow by Q&As towards the end, which you can either ask in person, or you can also type them in the chat, and I will moderate and towards Cristian. So without further ado, I'll ask my colleague Andrea to introduce our speaker for today. And with that, I thank you all.
Okay, thank you, Zach. So thank you, Cristian, for joining us. Cristian Axenie, after earning a PhD in neuroscience and robotics from Technical University of Munich in 2016, spent one more year with the TUM Center of Competence Neuroengineering as a research fellow before joining Huawei Research Center in Munich. Since 2017, Dr. Axenie is staff research engineer in AI and machine learning with the Intelligent Cloud Technologies Laboratory. At the same time, Dr. Axenie is a lecturer in AI and machine learning at Technical University of Ingolstadt, where he also leads the Audi Confucius Institute Ingolstadt Lab, a Sino-German research initiative focused on combining modern AI and VR technologies for applications ranging from sports technology to biomedical engineering. So then, without further ado, Cristian, the floor is yours. Thank you.
Thanks, Andrea and Zach, for the introduction and the opportunity to present our work. So I will take right now the industrial hat and will introduce you a bit on the work that we are doing in PhiML and physics and machine learning. So basically, we'll look at how to combine mechanistic modeling, nonlinear control, and neural learning for road traffic optimization. So within our lab, we work on optimizing traffic. And one of the technologies we developed with actually looking how can we benefit from the physics of traffic that we kind of all have a grasp on in our machine learning systems so that we can optimize that. So my talk today will be separated in first like framing the story, where and why we do this kind of work, and then going directly into the problem, the simplest level where we understand what physics needs machine learning, or machine learning needs the physics to be able to optimize such a complex, large-scale problems which traffic represents for us. Then I'll guide you through the details of how the system is implemented. We'll look at a bit of an evaluation, and then we draw some conclusions about our experience in how to design and actually deploy real-world system in real-world scenarios. So a bit of advertisement now, I admit. So basically, Huawei within the cloud business also develops a traffic intelligent twin system. So basically, we try to model and control traffic lights in large-scale scenarios. So right now, we are mainly focused on China, but we also have smaller scenarios in Europe. And we cover like 5 main areas, which is traffic prediction, road traffic analysis, accident monitoring, traffic kind of awareness, so traffic monitoring, and traffic light optimization, which I'll talk today and which is where physics meets machine learning in our work. And in order to kind of give you a bit of more framing for the discussion today, we'll look at real-time traffic signal scheduling, basically how to adjust the green time of the traffic lights, not in a single intersection, but in a large scale scenario, like a huge town like Shenzhen, for example, in order to improve the traffic flow through the town without creating jams, and how to adapt to eventual jams created by accidents, for example. And this is the work we'll look at, and this is where the lab where I'm working on focuses on. But aside that, we also have the data mining and the tracking and planning, which is a different business scenario in our company. But the work I'll present today is in fact work that we presented in ECML last year, and you can actually scan and get the paper for the full-blown details of the work I'll introduce today, with more of a spicy details for the talk today, which are focused for PhyML. So now that, like we set the frame, so we have a huge cloud service which runs some really fancy machine learning algorithms, which also borrow influence from physics. And we use this in large scale scenario at the moment, mainly in China, to control traffic. This is the problem we have at hand, a typical engineering problem. So if you look at a district level, so we have multiple crosses or multiple intersections, most of them signalized because we are in urban scenarios. And what happened, we have a multitude of sensors. So we have typically cameras, or we have induction loops to count how many cars pass, and we have the traffic lights to actually arbiter the flow of cars in all these streets. And now, given the amount of sensors we have, the typical pipeline, just to make sure we understand where the data flow comes into place. We have multiple intersections. We have multiple sensors, again, with different nature, being cameras, induction loops, or other type of count, or like other type of sensors for traffic. What happens, we collect these measurements, and then we have an estimation problem, basically try to estimate the traffic state. And then, of course, if you want to control that, to close the loop, to update the traffic light signals, we have a control algorithm. What we'll look at today will be mainly focusing on how can we adjust the traffic light system. So basically focus on the control algorithm, which takes into account the sensory data, a bit of physics information about how traffic looks like, basically a fundamental property of traffic, which is periodicity, and then try to close the loop on how can we calculate proper traffic light signals to obtain specific KPIs. I don't know, improve the flow and minimize the latency that car will wait at the traffic light and maximize the number of cars passing through an intersection. And now, if you want to get more specific, assuming a simple scenario. So now we have we have on a problem, our engineering table. So we have two crosses, a downstream cross and an upstream cross. So assuming that we have cars passing in this space-time diagram, which I depicted there, basically what happens is that you will have, for the sake of simplicity, I took out the amber phase, so the yellow light, I took it out. Just have red and green signals, which basically follow a periodic pattern. We'll have a certain amount of green and a certain amount of red, and this repeats itself. So basically, in order to make sure that we have a consistent flow of cars, we want to make sure that this platoon of cars go from the southbound to the upbound cross in this amount of overlapping green time. So basically, the cars need to travel this distance between the intersections with a certain speed to make sure they grab the green wave, so it allows them to go freely to the intersections. But this is already a hint to the aspect from physics of traffic, which we will focus on, which is the periodicity of the control signals that we find in traffic. And more precisely, we will look at this offset. Basically, what is the offset between two green phases? When I say green phases, basically, when does the green light start for a certain traffic light within the intersection? But But what you see here is unfortunately ideal. So this is what we will have in an ideal case where the time and space are properly defined and the speed of the cars is properly defined and the behaviors of the drivers are consistent and uniform, which is never the case in reality. And in order to give you a bit of more fine-grained understanding of this, what I mean with this physics of traffic, imagine you have this single intersection right now. So I'm going from the upper bound and going now the simplest case of a single intersection, where we have north, south, west, and east, basically corresponding to one of the traffic lights controlling the cars flowing in any of the directions. And what I wanted to mention earlier with this oscillation is basically, as you know, you will not be able to have green on all of the directions. So basically you have to alternate the green allocation on each of the 4 directions to allow the cars passing. So basically you'll have antagonist traffic lights on so that you can allow directions which are opposite to each other to pass, which is kind of intuitive and what we figured out many years ago when we developed the traffic light. But what I wanted to show you is basically a bit of the intuition about this single cross. So what we'll look at there is basically, you see some balls orbiting. So basically what we'll look at right now, we'll look at the phases of the traffic light. In more precise words, how and when the traffic lights get synchronized in terms of when they allocate their green. Because again, if you allocate green at the same time, you cause a mess, all cars come in, it's like non-signal intersection. Basically, remove the traffic lights, it's the same if you allocate green everywhere. So basically what we want to do is we want to harmonize when to allocate a green light for a certain direction such that we can maximize the flow of cars passing and of course, avoiding situations where you have accidents. So this is the problem at the smallest scenario that we can imagine. And now the question, how can we design a system which can benefit from this periodic dynamics of traffic light assignment and the fact that we have many cars passing in an urban scenario? So basically what we have here is a system which exploits the time, or it exploits multiple time series. For example, the number of cars passing from one direction to each other, from north to south, the flow of cars, the travel time from one side to the other side, and the amount of green time allocated for one of the traffic lights. Everything comes inside the system that we design and develop, and basically what the system does is try to extract these oscillations that we offer in the traffic light assignment, couple it with the fact that we have spatial correlations and temporal correlations. Basically, there are adjacent intersections, so they are spatially correlated. There's a distance between them, and also a time of travel of cars, because in towns we have limits of 50 kilometers per hour, 60 kilometers per hour max speed. So basically, we can actually infer that there will be a coupling between all these intersections. And this is actually a really important aspect and keyword, coupling. Because if we consider that each of the traffic lights acts as an oscillator, basically having this phase coming with a certain period to allocate green again, this allocation of green will have to kind of impact the allocation of green in upstream or downstream traffic lights from the one we consider. So in a nutshell, our system looks at traffic as a series of oscillators. Oscillations are physics phenomena which are observed many places in nature and also in technical systems. And we want to capture and exploit that. We want to capture the oscillations of traffic and the periodicity of the traffic light that we are controlling such that we can optimize traffic flow in a certain region. So we go away from the intersection and we aim at regions. And now looking at the system from a technical point of view, we just have to collect all these metrics I mentioned. So travel time, flow, green time. We have this oscillatory dynamics computation module, which actually exploits the periodicity of the signals. And then we have this prediction module, which will tell us when to allocate the green time for a certain traffic light at some moment in time. And additionally, we have the space and time correlation because of course, it's a finite graph that describes our network. And I think this is the most important slide of the talk, because from now on, we'll just go into the details. So basically, we talked about oscillators. So this is where physics come into play. And we have this rather long, but rather simple to understand equation, which describes the core of our physics part in the system. So basically, look at the system, we have some intrinsic properties and some extrinsic properties. So remember, in our case, from now on, we'll consider that each traffic light that controls the direction in an intersection is characterized by an oscillator. So each of the traffic lights has one of these equations behind it. Till now, everything is clear. And what this equation describes is, in fact, a typical Kuramoto oscillator. For those which are passionate about physics, they will know what that is. So it's an oscillator system, basically, which is characterized by an intrinsic property, which is the angular speed, basically how often you actually rotate, or like how fast you actually oscillate. Then we have some coupling strength. Keep in mind that we have a spatial coupling between the traffic lights, because there are adjacent intersections connected to each other through a street. Basically, this is what the network gives us. And this is where the coupling strength, which is A, showing the spatial coupling, and K showing the actual flow of cars passing from one intersection to the other. And aside this rather intuitive coupling, we also have some variability on top, which is typically brought by, for example, perturbations or rules imposed to the system. For example, that you cannot have a cycle time. Basically, a cycle is the sum of all green times allocated, and this cannot be larger than 120 seconds. So basically, all the green times allocated in each of the traffic lights, green lights, should not sum up over 120. So this is a restriction you put on your oscillator system. And of course, you also have, I don't know, velocity limits and so on. And the whole idea is that the output, this theta, is the amount of green time that a certain traffic light will be allocated. So now, if we take a step back, we think, okay, so, and each network has bounding points, intersections. Each intersection has 4 directions typically, and each one has the traffic light. Each of the traffic light has an oscillator. So you have multiple of these equations bound together in a system that you have to optimize such that you have a continuous amount of cars flowing and you avoid jams and time waiting in the queues. And for a simple scenario, let's look at this 5x5 network. So now we abstract away from the town, we look at a 5x5 network. So imagine each of the nodes in the network is an oscillator, basically following the equation I mentioned earlier. And if we look at panel A, this is actually the layout of the grid of our road network. Here in B, we have the dynamics. So as you notice, that's a differential equation that you can actually set initial conditions, and then it will evolve given the constraints and the coupling you have inside. And from the outside, it will converge to a consistent state. In our case, due to the coupling of the network, you'll see that after a while, starting from the initial state, after a while, if you actually simulate the differential equation, you'll see that we'll reach consensus. So basically, in a certain finite amount of time, all those oscillators characterizing our network will come into sync. So it will be phase sync or phase lock. So they'll be like in phase. And this is what we also see here. In a certain amount of time, the 25 oscillator characterizing our network here will be in sync. So basically, they will have a phase lock. Even more precise, when I say, what is this phase lock, or what is this kind of convergence? Basically, think about each oscillator has its own actually period of rotation, because you don't have to allocate green at the same time, because then you have a jam and everyone just smashes in the intersection. So basically, what we will have, which will be translated as more of a difference in time to synchronization. Because of the coupling, all the oscillators will synchronize to a phase lock. But there's another aspect. each of the oscillators, given the initial conditions, will need some time to reach that point. So basically what you see here in this time to synchronization or offset is how much time one of the oscillators will need to reach consensus with the others. And that's what we need, because this is exactly what we want to get. This is exactly the point where we say, okay, if we get this time to synchronization, then I know how offset I need to schedule a traffic light with respect to the others to be sure that I will not cause problems. Yeah, because I have already this finite horizon where I know the system will come to consensus. So in a nutshell, this is the dynamics that, or like, this is the type of dynamics we look at in this problem. So we want to explore the periodicity, and we want to make sure that we come up with a prediction when to schedule the green light such that we don't, or like we improve the traffic flow and we don't cause accidents. And now, because I wanted to give you again a more visual interpretation of all these oscillators, because it's typically it's hard to grasp. I got a test from Steven Strogat's website. It's pretty fantastic applet that emulates oscillators and so on, but it's made for physics students. So what I wanted to show you here is basically a simple visual understanding of what I mentioned earlier with this like 5x5 road network. So what you see here are like the phases of the 25 traffic lights. Basically, you have some variability showing how fast each of the oscillator rotates or like oscillates. These are the speed. Then you have the number, and then you have the coupling strength, how coupled they are to each other, and the angular speed. So basically, if you increase the variability, each one of them will spin at different velocity. You see some of them are faster, some of them are slower. Now, if we reduce it, it's the same speed. And now, when we increase the coupling, basically what we do, we just bring them to consensus. Basically, we bring them in phase lock. This is where we want, and given the phase lock, then we can measure how much time each of them needed, and then this is our offset to allocate to the green light allocation. So we try to tame some periodic dynamics by modifying the coupling strength of our oscillators. And now, if you look at the main problem, how do we do that? Well, basically what we do is to add a small part. So till now, this is oscillator dynamics, nothing new. We want to add a part which allows us to control how fast the oscillators come together. And in order to do that, we looked at nonlinear control. I will not go into detail, so if you want, we can take this offline because this is really a talk by itself. So looking at sliding mode control, so those doing a bit of control engineering, they know what kind of variable structure control this is. So basically, in a nutshell, we want to update the dynamics of each oscillator such that we can control it with a regularizing control law, so that to bring it to control how fast it will converge to consensus given the coupling constraints we have with the other oscillators in the network. And in a visual manner, so basically, given the initial conditions, what the control will do will push the system state towards the desired dynamics, which is phase lock in our case, which is given by this time of convergence or time to travel to the desired dynamics is the actual amount of time we want to allocate to the other oscillators to give green time in the traffic light. And now, because up till now, we saw that, okay, we have many differential equations coupled to each other and have some control. But Cristian, where's the learning part? Well, I just have to tell you that in our case in traffic control, well, we need to compute things pretty fast. Just simulating the differential equations and the control, it's actually not necessarily feasible in the time windows we have for aggregation and computing a new cycle for the traffic lights. And given the fact that we have up to 520 traffic lights in the region we simulate, yeah? So basically what we looked at is how can we accelerate the execution of this system, or how can we accelerate the simulation of these coupled oscillatory differential equations. And we looked at spiking neural networks as being a good approach for that. So again, in the simplest case, so basically what we want to do is to take the actual flow of cars or the actual inputs we have, because the flow of cars is known, we can measure it between intersections. And what we have right now, we have basically two populations. So we have a population of neurons which will encode the time series we have in distributed activity patterns of a population of neurons. So right now, think more about neurons as being dynamical systems themselves. So we look at spiking neurons, not at like the typical connectionist neurons. Yeah, and this is motivated basically to the real-time constraints that we have in our system to compute all the time a new phase for the traffic lights. And basically, what I wanted to emphasize with this figure is that we can use spiking neural networks to encode the quantities we have available, this time series, travel time, flow of cars, green time allocated that typically characterize one of the oscillators, and then do computation. So basically implement those equations for the oscillators in native neural oscillators. So as you know, I don't know how many of you work with the neural engineering framework or NANGO. It's a well-matured platform to do spiking computation, coming more from the neuromorphic engineering community. This is where I belong myself in the past. So basically, I look there as getting the substrate to do computation to be able to implement such oscillatory dynamics in an efficient way. And this is where it actually comes the machine learning part, because basically these systems are designed to optimize the representation and computation, representation of quantities like traffic flow and so on, characterizing the traffic light signal state, and do computation, basically implementing all this sliding mode control or the differential equations with the couplings themselves. And we have put such a system in place. And again, just to get an understanding. So basically we have the controller, it is a simple example. It's not even, it's a single oscillator. So the controller and the oscillator. So as you know, the oscillators basically have a recurrent connection. So basically you just get them initial conditions, then they will oscillate, kind of eating their own output. And then we have a controller that will try to guide that oscillator. And in simple words, this is a neural engineering framework or a NANGO implementation of a simplest intersection controller using oscillators in the sliding mode. And what we have here, as you see, you have two populations of neurons, and spike neurons, basically leaky integrated and fired neurons. And you see the oscillatory dynamics, and these are the spike patterns of the network. I would say in our case now, we can just abstract the spiking patterns, because what's important is to see that the controller has basically the power to alter the oscillatory behavior of the oscillator. So imagine this is a traffic light, and then we have a controller which will make sure that the traffic light will reach a certain desired dynamics or a certain desired state given the inputs it has and the controller to actually tame the dynamics inside. And as you see, with the controller, if we vary the actual stimulus, like external stimulus frequency, we can alter the oscillation dynamics internally. And what I wanted to emphasize with this example is that such an approach with spiking neural network was actually a better approach for our real-time constraints to recompute all the time for each traffic light, the green light allocation. So basically, this was mainly a design choice focused on really supporting the complexity of the modeling we have or the physics we want to capture using such a oscillatory system. And now, when it comes to evaluation, so this is what we had in our case. So we had one oscillator per direction. This is what you see here, the crosses. This is actually a scenario in Shenzhen, in China. And we have like 5 crosses with 4 directions and 3 crosses with 3 directions. So you see, you have different type of layout. And what you see here is just an example of flow of cars during a whole day. So how many cars passed in a normal day, and then how many cars passed, or in our case, how many cars passed when on a certain edge of this network, given there's an accident or weather conditions which are bad or rerouting due to problems. So basically, you see there are sometimes adverse effects in our data such that you have changes in the number of cars passing. And the reason is that we have different events which are unexpected, and the system that controls the traffic lights has to adapt to that. And this is why we had this control to make sure that it provides or brings all the traffic lights to consensus to be able to cope with such disturbances. And in another way to see it is also the time loss. So how much time the cars lost in traffic. So in our case, we have these two KPIs, the number of cars passing and the time loss. We want to optimize for that. Basically, we want to increase the number of cars passing and we want to minimize the time loss waiting at a traffic light. So this is just to give you a glimpse on how the disturbances in such a system look like. And now, more precisely, if you want to look at the evaluation, what I show you here is basically how the system does in normal traffic, the time loss under disruption without the control, and then the time loss with control. So what we have here, the orange, I think the orange is kind of a baseline. It's like the normal traffic is pretty smooth, and yeah, let's say around, I don't know, you have around 90 seconds loss in time. And without control, when we have disruptions, for example, an accident, basically you see that there are like these increases which are going up to 200% over like the norm, or even more when we have, for example, evenings. Yeah. So basically there's an accident and we have evenings, we have a huge amount of cars waiting in the traffic light at the traffic lights because of the events happening upstream or downstream. And with the control, we're able to basically adjust the traffic light signals such that we go away from these disruptions and we come closer and closer to normal flow of cars, despite the disruptions we have in traffic. And now how the control operates, basically you have all the oscillators provide an offset. So basically they calculate how far they have to be to each other. And this happens in two time scales. So basically you have a time scale which is slow, which is getting the data from the traffic. In our case happens every 5 minutes. And then you have a fast time scale, which allows the system to converge to a solution, basically to give us what's the green light to be allocated for the traffic light to actually optimize for the two criteria we have at hand. And then you have these two time scales working parallel to each other, the one which is the data coming from traffic, and the other one is the internal dynamics, which are accelerated in our case by the spiking neural networks to make sure we get in time a proper green light allocation. And now to wrap up, basically what we have here, we looked at ranking among different approaches. So this was more like for the ECML paper, this was more like a study that we demonstrated that we actually have gains with such a system. And we compared against the baseline, basically the traffic light plan given by police in Shenzhen. Then we have a multi-integer linear programming, which is the MIL. Then we have different implementations of the a system that we propose is obelisk system with spiking neural networks and without, basically just simulating the ODEs. Then we have a single oscillator basically modeling the whole network. And then we have two versions of ODE simulated and spiking simulated control version of our system. So with control and without control. So basically you even leave the system to us to come to consensus by itself, or you actually push it to consensus faster using the regularizing control. And these are the 5 metrics to look at. So the duration, basically how long does the trip last in the horizon of space we looked at, the region we looked at, the 8 intersections, what's the route length, the speed, the time loss, and the waiting time. Yeah. And so basically what we noticed here is that the best, at least the best ranking was this robust control implementing a spiking neural network. Although you saw for some metrics, the ODE simulation did as well as the spiking neural network. Basically, for those metrics, which are, let's put it this way, which are changing fast enough, the ODE simulation was also pretty capable. So the two versions here come hand in hand for at least the speed and the duration, for example. And another aspect which was also very important for us was the runtime. So basically, for a single cross, this was the runtime. Basically, the time needed from input data to the solution. So this is in seconds for the multi-integer linear programming, for the oscillator, for the integrated simulated ODEs, and for the spiking neural networks. And this is for the region that we showed with 8 crosses. So basically, we were able to gain 1 order of magnitude in the runtime over the other implementations with the spiking neural network, due to the fact that we exploit the dynamics also at the simple computational unit level, at the neuron level. And as info, this ran on a system, it used Flink as a distributed system management engine. So we had a cluster of computers, not on a single computer. So this is just more for those techies which want to know the data engineering behind. And with this, I would like to actually conclude. So what I wanted to show you today was that modeling is a fundamental dimension for controlling such large-scale systems. And in our case, the network of oscillators were able to capture both time and space interactions among different intersections in a network. And in order to cope with the unexpected traffic disruptions, we need to control that. So basically, to ensure that the system will reach consensus fast enough so that we can adapt to that. And in our case, this sliding mode control is like a robust nonlinear control, enhance the adaptation capabilities to handle this high magnitude, high frequency disruptions. You saw the number of cars changes in the short amount of time. And in our case, the machine learning actually supported such a modeling and control effort, such that we can bring the real-time constraints of the system to Earth, and actually having a system which is able to bring us there and calculating the traffic light signals fast enough and be able to react to disruptions in traffic. Implementing, of course, natively such oscillating dynamics. And we overcome state-of-the-art approach, at least for the small scenario we had and the metrics we looked at. And overall, like as a punchline conclusion, traffic control is a really hard problem, and many people try to tackle it in different ways. And we are not close to become to be the best solution, but we are happy that given the unlimited power of the cloud and such a physics-informed machine learning system, we're able to get good performance even on let's say, small scale, like 8 intersection scenarios that I presented. And with this, I would like to thank you for your attention, and hopefully the overall presentation was clear, but really, if you want, just check out the paper and you can get more details about the technicalities. Thanks a lot.
Thank you very much, Cristian. That was extremely intriguing. I really enjoyed that. In the meantime, if anybody has any questions, please submit them in the chat box, or you can, of course, unmute yourself and ask in person. I particularly enjoy the fact that there's, you're catering for disruptions in traffic, but also you're catering for human behavior, right, which sometimes is unpredictable. So thanks sort of to this hybrid situation between control system and data models, you're able to also cater as you go along. What I wanted to ask you was, which I think which I did, maybe I missed, is so the modeling part, is that updated when new data is presented to it? Is it are you reusing the previous model, or are you learning that part of the model from scratch?
That's a really good question. In fact, this was a really discussion also in our case. I would say, short answer, we are actually reusing, so we are restarting the model. So we are not reusing the previous model. Yeah. So we are not doing this incremental approach of like, okay, I use the final state of the previous simulation as initial state of the next one. Yeah, so I get the new data, and this data is the initial state of this oscillation. Then you go given this data and the coupling you have to converge to the new solution, and so on and so forth. And that's because we have all the flows available, because basically we have the sensors providing us how many cars pass in each of the intersections. So we can basically safely assume that each of the oscillators will basically need only the current sample of the vector. At time t, you need the current vector of all the values. For example, flow in intersection north, flow intersection south, flow intersection east, flow intersection west, given that northwest, southeast are connected spatially, and we have the data available. So for updating oscillator north, we have all the data available, so you start from this as initial condition. Right. So you always do this starting from the current data you have, but not reusing the previous model.
Right. And, I mean, yes, sir.
This helps us actually capturing such disruptions, yeah? Because, you know, there are two aspects of this kind of real-time or streaming computation. Is basically you can have also concept drift. And concept says that the norm of your data actually changed, yeah? So assuming that you have data which is mean at like 0.5, after some time, your mean will go at 1. And this is your new normal. Basically, you have to capture this like steep derivative, but then you have to adapt to the new norm. And if you keep all the old models, this will decrease your performance because you still have the impact of previous samples too strong in your prediction.
Thank you very much. So I'm wondering if there's any questions. In the meantime, I have maybe one small question. You know, like in most literature, the dealing with sort of physics enhanced machine learning, the benchmark tends also to be like complete black box model, right? And I wonder if you've done something like that in comparison. So without eliminating sort of the you know, this fusion between the dynamics, physics-driven dynamics, and also the data modeling in your case, whether you've done a comparison with one that is purely data-driven.
Purely data-driven.
Yeah.
I would say the only purely data-driven, which I consider, I think, but it's not even a machine learning, it's more of optimization, is the multi-integer linear programming, yeah? So it's a constraint optimization technique, basically, yeah?
Right.
So I would say that's the most kind of black box from my perspective. Although, of course, it's not black box in terms of, okay, there's a fancy neural network or a recurrent neural network doing the same thing. Although, in some other work of our team, we looked at exactly this spatial temporal graph neural networks. But, well, that was used for a different story to predict traffic. In our case here, we want to also do prediction and like control prediction.
Traffic, yeah.
So I would say no black box comparison. The best we had this constraint optimization.
Right.
Sure.
All right. So I think your presentation was extremely clear.
Maybe I can ask a small question.
Sure.
I'm not sure, Cristian, if you mentioned it, but I was wondering, so do your methods also suggest how to optimize the topology of the network? For instance, how and when to build new roads? Because I was thinking that maybe the problem with traffic can be solved simply to say, okay, like this is the current situation of affairs, but instead if we extend the network in this way, maybe we can solve the problem somehow.
Well, not explicitly, but basically, if you look at the dynamics, I'll just scroll there. That's a really good point, Andrea. Thank you for the questions. But basically, let's look at the model. So we had this coupling, yeah, this AIJ, which is basically an adjacency matrix. And then if you work out this adjacency matrix, saying that this also varies in time, yeah? And I would actually give you some insights in control engineering or traffic engineering. There's also the case that sometimes you reduce the pressure on some arterial edge, basically on a street, by opening other streets, basically to allow the cars to flow on other streets, overriding the local rule. For example, it's a one-way street. No, you override that, basically you allow the cars to flow to kind of release the pressure. And I would say the easiest adaptation to the model is to make AIJ depending on time as well. Yes, and then you can have changing spatial topologies.
No, yeah, I was, yeah, no, that's true. But I was wondering whether, because I mean, sometimes increasing the number of rows means to increase the dimension of the matrix A. So, but okay, apart from being the elements being time dependent, then you would also have the dimension being time dependent, which I think is yeah, I'm not sure how I would approach it. But yeah, so how can I say it was more a brainstorming question. Yeah.
I would say it's not necessarily a problem, because this is where the spiking neural networks come into play. Yeah. So basically, you can instantiate large populations of neurons, and this product, for example, this A times or Aij times sinus of these two phases basically will be implemented natively in two parallel, like two populations of neurons. One being the Aij, and the other one being implementing the operations of multiplication between the second one. The second one is the sinus applied to another one. So basically, I would say this dimensionality problem is coped in the implementation, in the native parallel implementation in populations of neuron spiking in the neural engineering framework. Yeah, because that's kind of the representation principle of the neural engineering framework, which allows us to implement like natively parallel computation. Yeah, and computation happens as between coupled populations of neurons encoding, representing distributedly a certain quantity we have at hand.
Okay, thank you.
Yeah, sure.
Right. So if there are no pressing questions, we can let you get on with your day, Cristian. I'd like to thank you so much for joining us today and for sharing with your work. I really enjoyed that. And we'd like to tell everybody to join us on our next seminar, which is in 2 weeks' time on the 21st of April. For more information, you can visit our website and for more details about that talk. So thank you all, and thanks again, Cristian.
Thanks for the opportunity. Excellent. Thanks for the question.
Pleasure.
Thanks, guys.
Thank you. Bye-bye.
Bye.